The last example we're going to see of a family of models is what we'll call the power models or power functions. And the reason that we call them that is that something is raised to a power. In fact, they're models of the form y as a function of x equals a times x to the power b. Now, the two numbers that describe this model are the a and the b here. And one thing to note is that that b, that exponent, is allowed to be any number. So before I show you an example, I want to take a minute and talk about what it means when we write a fraction in that exponent. You might have seen this in a previous math class, in which case this will be a review, or you might have never seen it before, in which case this will be an introduction. We know what x to the b power means when b is a positive integer, right? A counting number 1, 2, 3, 4. So x to the 4th means multiply together 4 copies of x. X to the 29th means multiply together 29 copies of x. Whatever it is we're multiplying by, we multiply together that many copies. Okay, what if b is a fraction? If b is a fraction whose numerator is 1, then x to that power, x to the 1 over something, means take that root of x. In other words, if we call the number x to the 1 over q, if we call that y, that means that number to the q power is what gives us x. So for example, if we have 81 to the 1/4 power, that gives us 3, because 3 to the 4th power is x. And these actual calculations, you can do the calculations on your calculator. We're seeing this so that we kind of know what it means when we're writing it. And then if we have any old fraction, well, we kind of combine those, right? If we have the fraction p over q, the denominator gives us the root, just like it did in 1 over q. And then the numerator, well, we just keep that as the exponent. So if we wanted to say 81 to the 3/4, right, that would be the 4th root of 81 to the 3rd. And we can do these in either order. This ends up being 3 to the 3rd, which is 27. Again, you can confirm that on your calculator. We can do the 4th root before the 3rd power if we want to. Those commute with each other. They happen at the same time in the order of operations. And then the last thing to deal with is if the exponent is negative, right, I'm going to write it with a negative sign just so it looks negative. X to the negative b means take the reciprocal. So for example, 3 to the negative 2 is 1 over 3 squared is 1/9. Now I've gone through this fairly quickly. In practice, if you ever forget what any of these are, you can work out the arithmetic on your calculator. And in practice, we're often going to have very unpleasant numbers in those exponents, so we'll actually want to use the calculator for our arithmetic. But I wanted to go over this because we're going to see some basic examples of power models, and we want to be able to do the basic arithmetic by hand. So, what are some examples? Well, we might have, for example, geometric area. So I'm going to go with a specific shape to talk about its area here. This shape is called an isosceles right triangle. It looks like that image, with the two sides labeled leg being the same length as each other. That little square in the corner indicates that this is a right triangle. That's a square corner. That's a 90-degree angle there. Its area follows this model. If the lengths of the legs of the triangle are 1 foot long, then the area of the whole triangle is 1/2 square foot. It's half of a square that's 1 foot on the side. If we double the lengths of the legs, the area is multiplied by 4. So I'm going to think of this as the area depends on the length. So the area is a function of the leg length, with if L is 1, A is 1/2, that's given to us. Then if we double the length of the leg, we multiply the area by 4. 1/2 times 4 is 2. If we double again, so the leg length is 4, the area is 2 times 4 is 8. So we notice that 4 is 2 to the 2nd power. This is going to be our power b in our model. And then, like the logarithmic functions, our starting point is where our length is 0. Not 0, 1, right? This is a 1, not a 0. Like the logarithmic models, our starting point is where our input variable is 1 rather than 0. For the same reason, right? Since we're multiplying our input variable, we don't want it to start at 0, because 0 times anything is still 0. We want to start at 1. So what we get here is that the area is our starting value, 1/2, times our leg length squared. This works for 4, right? A of 4 is 1/2 times 4 squared. It also works for numbers that aren't on the list, so we can ask, what will the area be if the leg length is 6? That's not going to show up in our table, right? Because the next leg length that shows up is 4 times 2 equals 8. But A of 6 is 1/2 times 6 squared. 6 squared is 36, times 1/2 is 18. So 18 square feet will be the area if the leg length is 6. Right, so whatever we're multiplying by on the left, it's some power of what we're multiplying by on the right, and we just need to figure out what power that is. That's the power in our model. These are really common sorts of physical models. If you take a physics class, you will see a lot of these models. The way we recognize these in a table is that we have a constant multiplication in both columns. So that's how we recognize these in a table. What about their growth rate? Remember, linear grows at a constant rate. Exponential grows faster the larger the output variable. Logarithmic grows slower the larger the output variable. What about these power models? Well, actually, the answer to that depends on the power. But it always sits somewhere in between the exponential and the linear. Excuse me. It always sits somewhere between the exponential and the logarithmic. So if it's growing faster when the output is larger, it's growing slower than an exponential would. If it's growing slower when the output is larger, it's growing faster than a logarithm would. So those are our four models. Linear, we had addition and addition. Exponentials, we had addition and multiplication. Logarithms, we had multiplication and addition. Powers, we had multiplication and multiplication. Those are the four models that show up in nature. Our next video, we're going to have a quick aside about a very common and popular family of functions that we're only going to talk about in this quick aside, but if I didn't mention them, you would wonder why not. And then we'll see why I haven't really told you how to actually get these equations. Did you notice that? I wrote down some equations from tables, but I didn't really tell you how to come up with them, the way that I did for the linear stuff last class. And there's a reason for that, and that is because the actual arithmetic involved is largely very unpleasant, and we're going to let the calculator handle it for us.